Hello, my name is Max Simbetta, and I am from New York, USA. I did my project on encoding colors in a quantum computer. Encoding colors in a quantum computer is good for the environment because it reduces and is easier and more efficient to use than a classical computer and therefore saves resources. In a camera surveillance system, the efficient use of feature selection in an image is required. Some of the main forms of feature selection is color selection, which utilizes RGB values of a video or image. Image recognition via color selection on a classical computer, however, is inefficient. On a quantum computer, which processes data in a different way, allowing it to perform far more efficiently than a classical computer, this may be a different case though. In my review of literature, the goal of the first article was to study the necessary requirements for classical computers to keep up with the increasingly more powerful AIs. OpenAI found that the amount of computational power used to train largest AI models had doubled every 3.4 months since 2012. This is a major reason why quantum computing is important, because it would enable us to keep up with our growing requirement for more powerful computers to run more powerful AI models. The goal of my second article was to build logical qubits for a quantum computer that are able to balance control and coupling with coherence. What this article found was that classical computers do not have enough processing power to run quantum problems, but a new computer is getting further developed called the quantum computer. The goal of my final review of literature, called Establishing Quantum Randomness, was to establish a difference between a qubit and a quantum bit via quantum randomness. What they found is that when flipping a virtual coin on a classical computer using a bit, the chance of it landing on either side is 50%. When a Hadamard gate is applied to a qubit and the same experiment is done, it results in a 50% chance. Further research had the coin flip twice on a classical and quantum computer. The program gave the same results for classical, but the quantum results, it showed a 99.3% chance of it being one side over the other. What this means is the randomness was undone, showing that qubits are different from classical bits because of their ability to undo randomness. My problem was, can color encoding be done more efficiently on a quantum computer than a classical computer? I believe that if color encoding is used in a quantum circuit, then a quantum computer can encode more efficiently than a classical computer, and my goal was to encode color into a quantum computer and test if color can be encoded more efficiently. In my experiment, the role of Student-Verse Mentor was for the student to create a quantum circuit for color selection, create images for use in testing, test the computer's color selecting capabilities, and create new tests for the computer. The role of mentor was to provide students with access to scholarly journals and articles, assist the construction of quantum circuit and programming, provide students with the resources to learn about topics and gain expertise, and provide professional opinions on features and algorithms. The first step of my experiment was quantum computing over the cloud. This is a step where the tools and requirements are covered. The first thing you will need is a computer or a laptop with the Qiskit software developer kit installed. You also need access to the IBM Quantum Services. The IBM Quantum Services provide real quantum computers that can be programmed over the cloud. You then want to use a system called Bogata on this IBM Quantum Services. Bogata is a 5-qubit system. You then want to select the best qubits on Bogata. These qubits were qubits 3 and 4 because they have the best T1 and T2 values. Higher T1 and T2 values mean more efficient, accurate statements. As you can see in this table, qubits 3 and 4 have higher T1 and T2 values. The next step is representing a picture via pixels. What we first did was we broke an image down into 2 pixels, and each pixel was made to represent a qubit. These were labeled qubit 0 and qubit 1. You then selected the colors and the combinations. The colors chosen for testing were the following 7 colors: Roy G. Biv, or red, orange, yellow, green, blue, indigo, and violet. Then 3 color combinations of these colors were also made. These were red, blue, yellow, violet, orange, indigo. You then use the function RGB to point to calculate a different number or theta value for each color. This will be how we can map and determine what a color is and encode it into the quantum computer. The third step was the quantum circuit for encoding color. The quantum circuit for encoding color is shown in the figure on the right, and each qubit represents one of 2 pixels. The value of the theta and the phase gate P for both pixels is set by the function RGB to point. We then ran the experiment for 10,000 shots or times to ensure we had accurate statistics. The phase was then measured using another function that converted the output of the quantum circuit into an estimated phase. The final step was to show that a quantum computer can encode and measure all colors. The true color image was used. This image was divided into 20 pixels, and each pixel was set 96 points apart, represented by the black lines. Then the theta value was taken for each color in this circuit and was placed and used. So as you can see, you could potentially use each of these theta values to estimate a color. The first step of my results was the single color image theta value comparison, in which both sides of the image were the same color. As you can see, the encoded theta and measured theta have about a 0.3% error, meaning that it is very accurate to encode colors on a quantum computer. The next result is the double color image theta value comparison, in which each side of the image is a different color. First off, you can see that theta values can be used to determine the differences in colors, as well as the fact that both images or both datas on the encoded and measured theta are very, very close to each other with, again, about a 0.3% error, meaning that encoding color on a quantum computer is highly efficient. The final result is the true color image theta value used to find the color. And this, you can see yet again that the encoded and measured theta values are very close to each other and have a low percent error, as well as that you can estimate the color with these values. For example, a color in the range of 1.94 to 1.36 could be seen as indigo, but if you were to take color in the range of 0.68 to 0.26, you could estimate that that would be blue. This is how we would construct a color wheel. RGB values have a unique theta value, and all these values can be mapped out on the said color wheel. These different numbers are referred to as theta or an angle, and these can be encoded into a single qubit using quantum phase with a phase gate. When comparing a qubit to a classical bit, only one color can be encoded per bit, but true color needs 24 bits. A single qubit can be used to encode true color, however, meaning that a single qubit is at minimum 24 times more powerful than a bit. When comparing the colors via breaking the picture into pixels, and each pixel being a qubit, one can tell if the image is blue/red, orange/indigo, or yellow/violet. And finally, in the final experiment, all colors were encoded into a quantum computer by breaking up an image of true color in 20 pixels. From the measured value in the first experiment, one is able to estimate the color and agreed with the image that was used for encoding. For future research, I would like to implement machine learning in a quantum circuit, use existing data to train a quantum computer to recognize data, and run tests to see if the AI can utilize the data we have now and tell the differences between colors. In conclusion, my problem was, can color encoding be done more efficiently on a quantum computer than a classical computer? And my goal was to encode color in a quantum computer and test if color can be encoded more efficiently. I believed that if color encoding is used in a quantum circuit, then a quantum computer can encode more efficiently than a classical computer. And my results showed that colors can be encoded into a quantum computer with far more efficiency than a classical computer. My name is Max Gambetta, and I'm from New York, USA, and I did my experiment on encoding colors in a quantum computer.